Okay, we're going to start. Homework 2 is finally graded. There's been a little bit of a hiccup with the reader and the hours it took to grade it. So it's here. I'll distribute it after class, and he's catching up with homework 3 as well. So hopefully Monday, Tuesday, you'll have homework 3 as well, just so it doesn't kind of completely evaporate from your brain. No, yeah. He got enough hours to do it. And of course, homework 3 and 4 should be easier, right? So hopefully he'll catch up. Okay, that's as far as homework is concerned. We're going to continue today to wrap up the biases and add the active loads. And that will help you when we move to the next section, which is going to be differential stages and then how those are loaded with the transistors and kind of intro into op-amps, because that's kind of where we're headed, both in terms of lectures as well as the lab. Lab 2 starts next week, so we'll start with diff pairs and then kind of build up toward the op-amp. Okay, so last time, just as a refresher, we sort of left it at the Such cascade, which was a nice way to go from two bias sources, currents that were needed in this low swing cascade, and maintain kind of the primary property, which was the low overdrive or the low headroom that's consumed by the output cascade stage, yet only use one current mirror and then this triode device to give us these intermediate bias voltages that are incremented by VOV, right? So that was kind of the primary goal. All the properties of Such cascade kind of remain here. So the systematic gain is 0, the output is GMRO square, etc. And you guys had I had the opportunity and the homework to do even one more stage of adding, so I'm not going to spend too much time on this. So what we're going to do today is move to the biases and active loads. But before I sort of dive into that, I just want to cover one more type of the current mirror, especially because we're going to be seeing it in sort of desirable and undesirable scenarios when we talk about biasing in general. And so this is a Widler current mirror. When I draw it, maybe some of you will recognize it. So I see laughs. Okay, so okay, so maybe we can go quickly through this one. What should be the R out for this one? R out is looking here. R naught. Okay. Any other? Everyone agrees, or any other opinions? If we had a simple output, right, then this would be R out equals RO, right? So here we have this constant thing where if there is a resistor of some form in the source and you're looking from the drain, you get something. Okay, so I'm hearing RO. What else? Parallel with R. Okay, any other suggestions? Okay, so if I replace this R with another transistor, for example. which GM? From which transistor? Okay, so there's GM2. And then it's RO. Okay, so RO2 times R, right? This doesn't sound familiar. So if I replace this R with the FET, then when I look from the top, I see something that should be familiar, right? I see a cascade. So in that case, what this guy really sees in the bottom is just RO1. Right? So this R becomes RO1. And we said that the formula for looking down, just because this one is active, right? So this one kind of amplifies this output impedance. So the formula for just the cascade output was what? There was some GM somewhere. So there was RO2, there was RO1, and there was something else. Yeah, that was GM2. There were some other terms like RO1, RO2 plus this whole thing, right? So, but we don't care. Approximately, it's this, right? So, and we said then, okay, approximately this was our GM RO square. Now, in this case, in the Whittler case, we don't have at the bottom R naught. We have R, which is kind of something we put there on purpose. So that's why you get this, plus you get sort of the RO. I don't know why this is happening. They promised it one. So you get some other term, but this is really the most important term over here. OK, so we do get some higher output impedance than just RO2. What about, let's quickly do the derivation. So here I have VGS1 has to be equal to VGS2 plus IOR, right? Because that's VGS2 and then a voltage drop on R. So I'll say if we ignore the body, in fact, it's just easier for me that way. So I can say that IOR and then the two threshold voltages will cancel out. So I only have equals VOV1 minus VOV2. These are just the overdrives. And the overdrives are proportional to a square root of the current, right? In this case, we're going to, OK, this is going to be the I ref, or I in, over K prime W over L1. And this one over here is 2IO over K prime W over L2. So if we know what I in we're pumping in and the W and the L's, since there is IO here and the square root of IO here, I can represent everything essentially as a quadratic equation, right? And then solve it directly for a square root of IO. And I'll just write it out here for completeness. There's also a thing in the book, and you've done it also in the homework, hopefully. So this is 2. And then the only solution that really makes sense is the one with the plus, simply because the square root of the current cannot be negative. So 2R, and then we're going to have 2 over K prime WL2. And I'll just write here, instead of writing this square root again of the I in, I'll just write 4R for our VOV1. Okay. So maybe wondering why is this interesting compared to the regular source? Well, the reason is exactly this difference over here. So what this allows me to do is, because I sort of have this voltage drop on R, suppress the amount of overdrive that I'm giving to M2 for given VGS1. That means that I'm sort of choking the output current intentionally. Okay? And in situations where I want to have very low biases, like, so let's say good low I/O, it's approximately microamps range. Okay, you know, current FETs have about half a milliamp per micron drive capability if they're fully overdriven, and so generating something in the microamps range is actually hard because you have to provide very low overdrive, and in very low overdrive conditions, there's a lot of variations that are happening. Plus, in order to do that, you'd have to, you know, if you go instead of I in and you replace it with a resistor like R1, that resistor would have to be very big so that you can kind of, if you were just directly mirroring the current, because you would have to have I in to be very small. Okay. So with Vidler, what you do is you kind of keep this R1 to be relatively small, so that your resistor area is small, but then you choke M2 and you get a lot less output current. Okay. So we'll see also that this type of phenomenon, this like resistance between this source and this ground, we'll also see it as a parasitic effect in a few slides down the road. Okay. So let's just take a look at some of the practical issues. So one big practical issue is, of course, the matching of transistors. We were relying on the fact that the diode device in the current mirror, which is the reference device, and the output one are nicely matched. So we looked at kind of the issues in W and L and kind of replicated. But even if you replicate identically the device, you have geometry variations, you have line edge roughness, you have random dopant fluctuations, so threshold will move around. So these transistors are not going to be exactly the same. And it's useful, sort of in the book, they go through kind of a little bit more of a derivation, but I'll just jot down the formula here for you that says that if I have essentially two devices, okay, one is here, and obviously in the mirrors, one will be somewhere. So I'm looking at these two identical devices that have W over L nominal sizes. Then the difference in the drain current over sort of the average drain current of the two will be and then will also depend on VOV. So the delta W over L is really the difference of the ratios. And it can be caused by difference in widths, difference in lengths, all sort of the geometric variations. And then W over L will be kind of the average. Same with threshold. And VOV, so VTH will be the average. And then VOV will be VGS, obviously, minus this average. So if we're biasing, and this is one of the key things that I mentioned earlier, if I'm biasing the transistor at very low overdrive voltage, then this factor here increases. What this means is that the effect of threshold variation will increase significantly at lower overdrives. That's sort of intuitive when we write out our quadratic current equations. You see that if your VGS is close to VTH, the impact of that VTH variation is going to be larger on that quadratic, right? So that's really what's happening in this term over here. And then here is just the, again, if I have a very big transistor, so W over L is really big, then the variation, of course, will be smaller, right? The relative variation will be smaller. So that's kind of represented here. In 240, you'll sort of go into the origins of the delta VTH and kind of how with area you can minimize that factor as well, which is kind of a constant over a square root of the area of the transistor and things like that. But this is just to give you a little bit of a feel what's happening. Another big thing, is, you know, even if with size you can overcome the variations, there is the question of, once you've generated these currents, how do you distribute them across the chip? Should you distribute this reference voltage around, or should you distribute this current around in case you need it in many different places, right? So let's say you have one, we did a pretty complex thing over here, maybe it's a switch cascade, who knows what, it's a pretty complex biasing circuit, and now I want to just distribute these heads around the chip, right? So if I do the voltage distribution, what I will want to do is take this essentially VGS, and then I can route it around the chip, and then in local places I can go and branch it out to a few local mirrors, outputs. This could be cascade, could be whatever, okay? So it's relatively easy to go and route, because I only need one wire to run it. It's a voltage, so it's into a gate. There's not a lot of drop over here on this resistor. Okay? But what's the problem with this scheme? Can anybody see? Mm-hmm. The more capacitance. Okay, so the comment is that the more traces you have, the more cap you're loading on this node, because there's more wire, right? That is true. And in situations where you're going to pass the signal here, yes, the bandwidth of this mirror would be lower, right? But if I'm looking at DC, right, things are on DC, I'm not that much affected by that, right? There's another thing that's just purely a DC issue. Mm-hmm. Voltage drops where? So there's no current going here except maybe a little bit of the gate leakage current, right? And okay, modern processes, that is also a little bit of an issue if you have a ton of recipients on that side, right? But there's something even more fundamental. Well, take a look at where this ground is and where this ground is. It could be 3 millimeters, 4 millimeters, 1 centimeter apart on a chip, right? And somehow it needs to come back. So it needs to come back in terms of the voltage reference loop, right? I want this VGS to be mapped over here, right? But I don't know where this current is flowing with respect to this potential over here, right? So for me to guarantee that this VGS1 is also dropped over here, I need to have this point firmly connected to this point. But that's not really possible if two grounds are, you know, a few millimeters apart. There will be some resistance in the supply network between this point potential and this potential. And there will be real ground current, at least some portion of this current flowing through this RS. Okay? So if that happens, what does this circuit remind you of? I have a diode connection here, and then where I'm mirroring, I have a resistor in the source. Yeah, the one we just analyzed, the Widlar source, right? So, or the Widlar current mirror. And what was this resistor doing there? Yes, it was choking up this transistor over here, right? So it was limiting, it was decreasing the current, because it was eating up into the total VGS of this output transistor. Okay, so this is obviously unintentional. You don't know what resistances are going to be. So it may be 2 ohms in one, it will be 10 in the other, and all these small changes will cause all these output currents, IO1 to IO10, to be essentially totally different by some amount. Okay, this is not random variation. This is sort of systematic issue, because once you build the grid, you know where things are going, but it's kind of hard to track. So in order to avoid these issues, you never do this type of routing scheme globally, where the length of these wires is very big. Okay, so you do it locally, where maybe you want to distribute locally to many places. There's a dozen little heads that you want to go, but you sort of use this one wire locally. But then you make sure that all these grounds are kind of very closely, tightly coupled. So this is voltage. Okay. So advantages would be here. Less dense, right? So can route more wires. And disadvantages will be variation due to RS. The other thing will be that obviously this transistor that's on one end of the chip and this transistor that is all the way on the other end of the chip, if I'm doing global routing, will be different. The geometries will be different, film thicknesses slightly, not to mention the random dopant fluctuations. But these two systematic things will sort of impact you. So will be transistor mismatch. We're going to have issues with these mostly with these factors over here on the geometry, right? And some part of the threshold variation that is due to systematic film thicknesses across the chip. So the alternative is the current routing. What you do is you'll have your reference as well as all the others that you need. You're going to have them all in one bank, right? Very, very closely, nicely coupled together. And what you'll route out is essentially just current bus. Now, you obviously see that, advantages are going to be matching, as well as no supply R, right? And disadvantage will be just lots of wires. In modern processes, wires are all that occupies the space. Transistors are just free things that fit under the wires. So you have to be careful where you want to do this. But you want to do it if things are global and you really do care about the precision. Right? So you do care that this eye really got mapped to each one of those. And so you do take special care to lay out this set of transistors. Okay, so more about that in like 240 and things like that. But I just wanted to show you a little bit, give you a little bit of a flavor. So in summary, sort of you would route currents globally and route voltages locally. Okay, that's kind of the morale here. Now, in addition to just routing stuff, we also want to control these current sources. We don't want them to always be on, because that's a lot of power consumption everywhere. So people usually design simple mechanisms to shut these devices off as controlled by the logic. So one scenario, one thing you can do is do it like this. Oops. Now, this can go on, right, to a whole string of these devices, and then you'll have a power down signal here and its inverse over here. Right? So you will both decouple the diode from the rest and then pull this node to ground. So all these are not leaking, they're all firmly shut off. Right. Now, you also want to do, or this was like, whatever, 2, supply filtering. If you have this directly connected to VDD, and for example, any source here would have its own R out, right? In the simplest case, I can replace this current source with just a resistor over here. Right? In that case, whatever's happening on VDD is directly modulating whatever this current is. And we'll see in the next few foils, I'll show you some of the supply-dependent and independent biasings. But inevitably, whatever you do on the supply will kind of map into this reference current. And that will then map to the output. So if you want to kind of filter that and get really nice, get just the DC to replicate, but these supply noise or supply blips to not replicate, you can add some filtering. And so let's say one way to do this is simply to add, similarly to the power down scheme, just add here a gate with V bias. And then we can add a FET here whose source and drain are connected together. That one will be sort of in the triode region in terms of because source and drain are connected together, so you're going to get don't get the pinch off. So now the whole cap here will be C prime aux WL, right? Instead of 2/3. So I'm getting a little bit more capacitance here. And then this goes into my reference device. So this transistor here acts as R, and this one acts as a C. Okay. So with this, we're going to move on to look at the full references. And the two key things for the references are, one, we already started mentioning, that is the supply independence. So that if I want a certain voltage, I'd like it to be sort of independent of what the chip supply fluctuations are. So I'm going to say and two will be temperature. So whenever you design chips, you will always kind of test functionality over process variations, supply, and temperature. And those are not just environmental conditions, but it's also heat cycles that the chip is going through. And things are very active, very hot. You're getting junction temperatures around 100, 120 degrees C. And then you can get them cooled down to -40 in some extreme environments. So over that whole range, things have to kind of work. And there's sort of civil spec and military spec, but those are kind of the ranges you're talking about. So let's take a look at this supply independent biasing. So let's do first an example of how not to do it. Right. And you may already know the answer to this. Right. This is our simplest current mirror. Right. And what I just did, I replaced the current source here with a resistor. Now, if this is VDD, I can actually go and derive what the output voltage value is going to be. Right. So we have, we'll say, okay, we'll still call this IREF. So IREF would really be VDD minus VGS1, so this is VGS1, over R. And then we know that VGS1 is V threshold plus the overdrive, and the overdrive is the square root of over K prime W over L. So, and then our output will be equal approximately, obviously, because of the difference in the drain source, but roughly IREF. And even if you don't look at this, so what you should see, even if we don't solve it, what you should see from here is that there will be a term, as in VDD. The first term is VDD over R, and the second term is minus VGS over R. And I can replace that with this square root, again, of the IREF. So it will be some square root, and IREF is, again, a function of VDD. So it will be some constant here, C times VDD, blah, blah. Okay? So what I'm trying to show you is that the dependence of I naught on VDD will be linear here, and then some square rootish term, et cetera, that's less important. Okay? So this is really bad. Whatever happens in VDD, you directly see it at the output, right? Because this VGS is less quickly reacting to a change in voltage, in the supply voltage. VGS reacts to a change in current only as a square root, right? And therefore, if I change VDD up, the current will change linearly, just because this guy changes only kind of as a square root of current. Right? So this VGS will change much slower than VDD. Okay? But that will reflect altogether on I out. So given this, given that VGS changes much more slowly than the current itself, do you have any ideas how we could do it differently? What could we use to be our voltage reference instead of the supply? Okay, thermal voltage is a good idea. I will show a few designs later, but you would need to have sort of a bipolar kind of parasitics and things like that. But if you're lazy to do that, you don't want to really kind of mess with kind of building a band gap reference, what can you do quickly here in terms of MOSFETs? If I know that my reference current is going to change linearly with VDD, but my VGS is not, right? Can I use VGS as the bias, the reference itself? So I do double cascade, right? I will first generate the current from VDD. I know that current is really not that good. It's very sensitive to VDD. But then the VGS that gets derived off of that current will be less sensitive to VDD. And then I can derive another current off of that VGS. See what I'm saying? So here's how it works. So we start from VDD. And we're going to say, well, there is an R here. And so let's call R1, R2. And then I'll have my output transistor be like this. So take a look now what's happening. My I out is a function of what? Is there any current here? No. So I out, all that comes in here goes here, right? So I out is also here. So I out times R2, what is that voltage? That's VGS1, right? So my I out is really just determined by VGS1 and R2. This is now my voltage reference. Okay. Now IREF, I write it as is our VDD minus VGS2, which is this drop over here, and then minus VGS1 over R1. So IREF is still kind of changing very quickly with VDD because of this relationship, but I out is now only a function of VGS, and we know VGS changes as a square root of IREF. Right? So it will change sort of as a square root of VDD as well. Okay? So we'll write it. So VOV1 is K prime W over L. So if you take a look at IO, it's proportional to VGS1, which means it's proportional to square root of IREF. And that means it's proportional to a square root of VDD from here. So we've turned something that was previously linearly proportional to VDD into something that's a square root of VDD. Now, that's pretty good. Okay? Now, if you use bipolars, you can do even better, right? Because what's the relationship of VBE and current? Yeah, or in other terms, let's say for BJTs, you would have that I naught is proportional to the log of VBE, right? Or I'll just put VDD here. There will be something else over here, but that's what you get. So instead of a square root, which comes from inverse quadratic dependence, here you'll get an inverse exponential, should be a log. Okay, so this is a simple trick you can use to kind of get a little bit more robustness to supply voltage variations. Okay. So another, as we said, issue is this temperature. And this is really kind of more advanced topic. So previously, it was kind of left for reading for grad students. I'll try to distill it here a little bit just for everybody to kind of understand. So I'm omitting a lot of math. But if you're really math savvy, there's a lot of it in chapter 4. So bear with me a little bit. I just want to give you a gist. So for temperature independence, we really want to, since we have MOSFETs, and on the other hand, we have the maybe parasitic bipolars in the same process through NWell, et cetera. We sort of have the VBE as well as the VT. And if you look at the, these two types of voltages, after a long derivation, you can figure out that the sensitivity of VBE to temperature is somewhere around -2 millivolts per Kelvin, or per degree C. Okay? So if you contrast that with dVT, which is the thermal voltage, okay? This is just K over Q, right? And K over Q, if you plug in the numbers, you get around 0.086 millivolts per Kelvin. So the key thing here is that this piece has a negative sign. And this piece over here has the positive sign. So I have two voltages in my, that are sort of naturally occurring in my circuit that have different gradients with respect to temperature. And what a circuit designer does, it sort of adjusts these two so that the when they get summed together, the gradient goes to 0. Okay, so that's the whole story about the temperature-independent reference sources, right? So the way you can do that is, I'll just draw it first conceptually. So you can have a current source here in NWell, or here I'll just show you the real. I'll pretend I have an NMOS. Okay, so this is my VBE, and the slope here was minus 2 millivolts per Kelvin. And I'll take that, and then I'll have here something that I'll conceptually call VT generator. And this will give me here plus 0.086 millivolts per Kelvin. Then I'll multiply this up with some, let me draw the amplifier shape just so. And then I'll add the two together and get V out with slope that's approximately 0. So V out will be equal to my VBE plus M times VT, where M is some gain. It's a fixed factor, 5, 10, we'll see. Okay. Obviously, by multiplying up VT, I'm also multiplying up its slope, right? So if I do a derivative, I'll get my dVBE dt, and I'll get M times dVT dt, right? So I'm using this M to multiply up 0.086 so that it matches with 2, right? Just the opposite sign. And if you work out the math, for complete cancellation, M would have to be around 23. Now, in practice, for various reasons of sort of second-order dependencies, you're not going to be multiplying up this high, okay? Especially because of the this amplifier will have sort of an offset. And when you multiply the offset with a very large number, this will kind of skew the balance. So you're not going to have compensation across the whole temperature range. So we'll see a little bit here how to go overcome that. But this is basically the main gist. So in CMOS, how we would do it a little bit more explicitly, let me just draw it, is we would have R2, R3. We're doing nothing else but realizing this scheme that already talked about. Okay, and then you're going to have an R1 here. Okay, and then I'm going to draw okay, so we'll label these as Q2 and Q1. So if I have essentially a circuit here, that's my amplifier. I'm tying it in a negative feedback through R2 and R3. And then I have my VBE, but I also have, or this is the VB, and then I also have the difference of the two VBEs to give me VT. And how's that going on? So let's first take a look at what is the delta VEB. So let's say VEB, we can do 1 minus VEB2. And VEB1 will be VT ln of I1 over IS1 minus VT ln I2 over IS2. Right? So these are all just our bipolar equations. We use P and P's here simply because in an N-well process, I have an N-well, that's my base, and then I have the P contact, and so that, and then the P substrate, and that's my PNP transistor. Right? So that's what I'm going to be using in a MOS process. And then this is really just VT ln of I1 over I2 times IS1 over IS2 over IS1. Right? And as long as I'm dictating these currents through these, so this will be my V out. So these currents will be dependent on V out over this resistive divider. So these are well determined. But what I really have is that delta VEB is proportional to VT. So that's my VT generator. Okay? I can consider this to be gain. This is not going to be the only gain, but it's going to be part of the gain. And actually, as you'll see, a very important part. Okay, so once we know that we can use the difference of the two EBs to get us the VT generator, now let's see how we can solve exactly for the V out. So first thing, we're going to look at this VR2 and VR3. So we're going to say that VR2 is R2 over R3, VR3, because there's no current flowing here. So same current is flowing through both. And then just for VR3, we have this KVL loop over here that is VEB1. So that's this. This is VEB2. So we have VEB1, and then we're using the negative feedback property that V plus equals V minus. So then we have the offset voltage of the op amp, and then we have VEB2 minus VEB2. Okay. So then our VR2 is equal to R2 over R3. We have the difference of our two VEBs. So we're going to call that VEB, delta VEB, just like above, plus VOS. Okay, so our V out is going to be VEB2 plus these two voltages, VR2, VR3, right? plus VR2 plus VR3. And since they're related with R2 over R3, I can just write VEB2 plus 1 plus R2 over R3 times this delta VEB plus VOS. Okay, so look at this beautiful expression. It's exactly what we had previously in this conceptual thing, right? We had the VEB, which would give us our negative temperature coefficient. And we had a factor that I'm going to call here M prime. We had a gain factor, right? And then we said the delta VEB, so for VOS equals 0. So if there was no offset voltage, then this delta VEB, we said, was VT ln of something, of a constant here. So then this M prime times the log will give us our M. So that will be the total gain. And the gain is on VT. Right, so it's exactly that equation. Now, what's really happening here is that with this type of circuit, we've kind of separated out a little bit this gain M prime with which we multiply the offset voltage from the total gain on VT. Right? You see that only 1 plus R2 over R3 multiplies the offset voltage. But we also have this extra gain factor from the log that multiplies the VT. So what we want to do here is we don't want to multiply the offset too much because that introduces the error. So when we trim these resistors to get the zero slope, if the offset was already there, we're a little bit off, right? So what we want to have is something where ideally we don't multiply the offset voltage with anything, but we just multiply the VT, right? And so we achieve that by sizing these two transistors in such a way that this ratio of currents that flows through them and the ratio of the leakage currents is giving us positive gain. So an example is that we're going to use I1 greater than I2. I1 will be approximately 10 times, let's say, I2. And we can do that by tweaking our R2 and R3 in series with respect to R1, right? So that should be relatively easy. So tweak. If I increase both R2 and R3, then I'm not really affecting R2 over R3, but I'm changing I1 versus I2. And then what I'm going to use is I need IS2 to be bigger than IS1, which means that the emitter area of transistor 2 will be bigger than 1. So I'm taking a small current and pumping it into a big transistor. And then on the other hand, I'm taking big current and pumping it into a small transistor. Okay, and through that, I'm getting sort of the max possible difference in their VB voltages, which to the first order, you remember we said they're roughly 0.7, right? So we're trying to spread that a little bit. And then amplify that by this. So when you do these tricks, if this is, again, A2 is approximately 10 times area 1, from the log of 100 times VT, you can get approximately, let's say, 120 millivolts, right? About a factor of 5x amplification. And then that leaves you maybe another 5x 5 to 6x on this. And that should be OK. So those are typical kind of sizings that we want. OK. I guess we're kind of out of time. There's just a little bit more